Okay, so we got a problem here that we're going to look at today. We want to find the displacement at C in the middle of this beam. Now we could do it a couple different ways. The techniques that we've talked about so far, we could use direct integration. So if we were to use direct integration, how do we solve this problem? Could I write a continuous moment equation across the whole beam? No. So I'd have to write an equation valid from 0 to 10, and then a second one from 10 to 40, and then I would generate 4 integration constants. I'd have a couple of interesting things to do. Have to solve some simultaneous equations. Could do it, and then I could just plug in x equal 20 and get it. Easy enough. I could use conjugate beam. You might imagine that the moment diagram for this particular structure would be linear, and that might not be a bad problem. In fact, I think we worked a problem very similar to this using conjugate beam a while back. So to compare and contrast a bit, we're going to work a problem like this again, but this time we're going to use virtual work. Now, virtual work does share some things in that I do have to write moment equations for this structure. And this is the real loading, so I'm going to have to write 2. One's going to be good from 0 to 10, a second from 10 to 40, and then I have to write the virtual system and then write the equations for that. So that's the procedure. So let's go ahead and get started. So we're going to start with the real system. Which is what's drawn here. So in order to write these equations, I'm going to need the reactions. So let's start here with, I'll assume AY acts up and DY also acts up. So let's get those reactions first. I'm going to sum moments about point D and make sure it's in equilibrium. By doing that, I should be able to find my reaction at A. So summing moments about D, the applied load of 15 kips creates what kind of moment about D? Positive or negative? Positive. So we'll have the force, 16 kips, times the distance from D to that force, which is 30 feet. And in balancing that is the moment caused by A, which is acting up, which creates negative moment, and has a moment arm of the distance between A and D, which is 40 feet. So I should be able to solve for AY. It looks like it's 12. Does that sound right? So that's 12 kips. And then, to find DY, I can quickly sum forces in the Y direction and find that. So I see that AY is acting up on my free body diagram. DY is also up, and then I have my 16 kips acting down. So it looks like DY is 4 kips. Okay? So in my real system, I want to write a moment equation that's valid for the first 10 feet. So that would be a system that looks like that. So this is X, and that can be anywhere between 0 and 10. I've got positive shear and positive bending moment at the cut. And then, of course, at A, I found that my reaction was 12, and I assumed up, so the force is acting up of 12 kips. So there's my free body diagram for that. Now, right now in virtual work, we're not including the energy due to shear. We're only including the energy due to moment. So we're not going to really worry about the shear. So with that, I'm going to sum the moments at my cut. Make sure it's in equilibrium. And what do I have? I'm using right-hand rule for my sign convention, so the internal moment at the cut is positive. And then a moment about the cut due to the 12 kip force is what? Positive or negative? Negative. And that would be minus 12 kips times x. So it's pretty easy to see that the moment here It's just 12x. So that's the equation for moment from 0 to 10. Now what about from 10 to 40? Well, I need to cut the structure here, and I'll just put my little triangle there. So if I cut the structure here, what side do you want to look at? The left side or the right side? Looks like the right side is going to be a lot easier. So I'll do that. So I'll make a cut of the right side of that. Remember that the distance to the cut is still x. That means the remaining piece of my structure, this little segment, would be the length 40 minus x. And then again, I have internally my positive moment, my positive shear, and then over here on the right side, which is dy, I have 4 kips. So again, we're not concerned about shear. We're only interested in moment. So now I'll come down here, and I will sum moments at the cut. Make sure it's in equilibrium. So with right-hand rule as my sign convention, this positive bending moment is actually negative, and the moment due to this 4 kip force is positive. And that would be 4 kips times 40 minus x. So again, you can see the moment in this structure will be basically 4 times 40 minus x. I'll go ahead and multiply that out, and it's 160 minus 4x. Now before we proceed, we can do a couple of quick checks. In this structure, we know the moment a couple places. We know the moment at A. What's the moment at A? 0, okay? So A is at x equals 0, and this is the equation that's valid for that. And I put in x equals 0, and I do get a moment of 0. That's good. We also know the moment over here at D. What's the moment at D? 0. That's at x equals 40, so I have to use this equation that's valid for 40. And I plug in x equals 40, and I get 0. Great. I also know that where the two moment equations meet, and there's not an applied moment, they should have the same value, and that should be at x equals 10. So I put in x equals 10 here, I get 120. I put x equals 10 here, I get 120. So I feel pretty comfortable that my moment equations are right. So I'm about halfway through the problem. And you might recall that in exam 1, or the first part of the course, we would be finished. And now we're not. We're only halfway. So let me kind of put a little line here to break that off. And now let's look at our virtual system. So I'm going to draw the beam again. So the supports are the same. I still have a pin at A and a roller at D. Now, for the virtual system, I'm going to remove the real loads, which I've done here, and I'm going to apply a virtual load at the point I want the displacement and in the direction I think it's going to occur. Well, that's pretty easy. It says I want the displacement at C. C is right here in the middle, so I'm going to put my unit load right in the middle at point C. And I'm going to say it's down, which means I'm going to assume my displacement is down. And looking at this real load, you can expect the structure to deflect down. So I'm also expecting to get a positive result. So let me go ahead and write this is 20 feet and 20 feet. So now it's like, okay, I have a new problem to do, this problem. And I want to find equations for moment in this problem. With that said, I have to recalculate AY and dy. So I'll do that. So I'll sum moments about D again. Make sure it's equilibrium. So starting about D, I have the unit load That's creating positive moment, has a length of 1, or a value of 1, and then 20 feet, a 20-foot moment arm. And then AY creates negative moment and has a moment arm of 40 feet. So surprise, surprise, AY is equal to a half. Has no unit because this has no unit. And I don't think that's a surprising result. A simple supported beam, a load in the middle. We expect half the load to one side, half the load to the other side. So far we've got that. And this may seem a little redundant, but we'll do it anyway. We'll go ahead and sum the forces in the y direction. So I've got AY up plus DY up minus 1. So I know DY is also a half. So far, so good? Now I have to write moment equations for this. So in this scenario, I have, again, I cannot write an equation for a moment that is consistent throughout the whole structure, right? I have to break it up. So I'm going to write one that's good from 0 to 20, and a second one that's good from 20 to 40. So let's look at that first one, the one from 0 to 20. I'm going to cut the structure here. I think you can see if I cut it that the left side is easier to deal with than the right side. So I'll draw a little free body diagram of that left side. My reaction is a half. I have positive shear, positive bending moment. So again, if I sum moments about the cut. Oh, I left out something, I'm sorry. This is distance x. So I have the moment, which is positive, and then I have this, which is negative, and that has a value of 1/2 times the distance of x. And I did make a mistake. This is not the real moment. This is the virtual moment. So I should use a lowercase value, right, just to distinguish the two. So I'm going to scratch this out and write it as a lowercase m. So now the lowercase moment is going to be x over 2, the virtual moment. So I'm trying to distinguish between the real moments using uppercase and the virtual using lowercase. So I have one more segment to do from 20 to 40. And again, if I cut the structure, left side, right side, looks like the right side is going to be a little easier to do. So I'll draw a section for that. So this will be good from 20 to 40. So there's the right side. Again, it'll be a distance x up to the cut. This section will also be 40 minus x. Here at D, I have a half. And then there's my positive virtual moment. So again, if we sum moments at the cut, make sure I have equilibrium. This internal moment is negative. The moment about the cut due to the 1/2 is positive, and that's going to be 1/2 times 40 minus x. So the virtual moment here will be this value. So I take the 1/2 in, that gives me 20 minus x over 2. That's one way to do it. And again, I can check those, right? I know that the moment at A should be 0. And this is the equation that lets me have x equals 0. And I plug in x equals 0, I get 0. I know the moment at D should be 0. That's when x is equal to 40. So I go down and use my Fourier equation. I put in x equal 40. I get 0. And I also know the moment should match at 20. So I plug in 20 here, I get 10. I plug in 20 here, I get 10. So it seems like all my moments are good. So really, at this point, all the hard work is done. So now to form the virtual work expression, I'll try to squeeze that in here. So according to that, the displacement at C, by definition, is the integral over the length of the real moment times the virtual moment divided by EI times dx. Now here's the tricky part. None of my equations go the entire length. Right? I have a real moment that goes from 0 to 10, so I have to match that with the virtual moment that goes from 0 to 10. And that's this equation here. So this is going to end up being an integral from 0 to 10 of what? The real moment, m, which is 12x, times the virtual moment, which is x over 2, divided by EI dx. Okay? Plus, what comes next? Well, now I have to start at 10 and go forward. So if I go from 10 to where? Well, anything greater than 10 in the real moment is this expression. But this equation is still valid till 20. So I've got to go from 10 to 20. And when I do that, I have to use my different real moment, which I've computed as 160 minus 4x, again, times this same virtual moment, x over 2. And again, divided by EI. dx. Now what's next? Well, I got to go from 20 to 40. Well, this is good from 20 to 40. Oh, and this one's good from 20 to 40. So I can match those. So the next integral will go from 20 to 40. In that case, the real moment is 160 minus 4x. And the virtual moment is 20 minus x over 2, divided by EI. Now for me, on the exam, that's going to be good enough. Because these are polynomials, and if you had enough time, you could expand them, you could integrate them, you could evaluate them. But you can see the evaluation is pretty tedious, and there's all kind of room for error. Now, that's the good part about the exam, is that this would be good enough. And if you had time, I would allow you to complete this and actually put in the values for E and I and compute a numerical value for some bonus. But unfortunately, in mastering engineering, you still got a lot of work to do. They're going to ask you to complete the integrations, plug in E and I, and then enter the value.
If we get it wrong, we're not going to get any points off.
Get what wrong?
The bonus.
Well, this is all I'm going to ask you to do right here. So if you get that, you've just gotten 25 out of 25 on that problem. If you have some time and you're sitting around, hey, I got 5 minutes left in the class, I'm finished. Go back and do that. I'll give you some extra points. Don't bank on that to save you from a poor performance on another problem, though. So what I'll do for right now is I'll go back to my office and I'll finish this out. And when I publish this problem as a PDF, you'll see me finish this up and give you a numerical value. But I think for our discussions here today, it's good enough.
What did you say that last column was? The virtual what?
I'm calling it the virtual work equation. This is the general virtual work equation. This is just in general. But now you've actually filled it in with the values that are appropriate for this problem. And that's the work. At this point, you're just an integration monkey. Okay,